Okay, so now that we've sort of introduced Newton's third law, I want to talk about tension and ropes and pulleys. And adding ropes and pulleys to, the amount of stuff we can do really gives us some really complicated and, in my opinion, very fun problems. So let's quickly remind ourselves of the role of tension. A lot of this is in the textbook, and so I don't want to spend too much time on it. But so the idea, okay, so person, maybe, geez. Of course, once I start recording is when the lecture just goes bad. Okay. So this is like their hand, right? Okay, something like that. You're pulling on a rope on a wall, and it's not even attached to the wall. Okay. What is tension anyway? Okay, if the tension is the fact that these microscopic bonds stretch, every point on there. And so what does the rope feel? If you draw a free body diagram of the rope, right, there's three things going on here. There's the person, right? The person's, so the rope feels a pull. So this is like a tension force. But then the third law says that the rope pulls back on the person. So that's a little action-reaction pair. That's Newton's third law. The definition of tension. What if there was no force on the left-hand side? Then the rope would accelerate. But it doesn't do that. So there has to be a force on the other side, equal and opposite. And then that's the tension force of maybe the rope on the wall. And so the wall in turn is pulling, feels a pull by the rope. That's the tension of the rope on the wall. Let me flip that. Okay. So that's the definition of tension, is that it's the same force that is felt at every location on the rope. And technically, that's correct for if you assume that the rope is massless. And so what I want to do is, okay, that's tension, and then I'll usually assume that the rope is massless. I think for all of your homework problems in chapter 7, and there are a lot of them, you will assume that the rope is massless. Now, I want to consider a little bit harder of an example, and this, kind of like the drag stuff we did, this is a good example of practicing reasoning about pulleys. So we got a rope that's attached to the end, and then there's a pulley here, and there's a hanging mass. I want to go through systematically what the forces are. So this is not something that is in the videos, but it's a little bit more detailed on how pulleys work. We'll always assume, at least for now, that the pulleys are massless and frictionless. And so what are the forces acting on the rope at this point? Well, let's look at, okay, this is a wall. So rope is pretty well anchored to the wall. So the block on the bottom here is not going to accelerate. So what's the free body diagram on the block? Downward gravity, mg, and then upward tension force. There's lots of vectors here. Okay, and those equal, right? Fnet is 0 for everything in this example. Nothing's moving. Now, okay, so there's like three pieces to consider. There's the downward part of the rope, there's the pulley, and there's the point where the rope moves or rotates, and then there's the wall. So let's look at this downward part of the rope. The downward part of the rope, it's going to feel a downward pull from Newton's third law. But it's also going to have to feel an upward pull on the pulley by the definition of tension. Okay, so this downward arrow and this upward arrow represent the definition of tension on the rope. Well, what is this upward tension vector going to do? This represents the tension of the pulley on the rope. Okay, obviously on the pulley, then the pulley is going to feel a downward force. The pulley itself will feel a tension of the rope on the pulley. So this is by Newton's third law. So you have the simple example of tension and gravity for the block, and then you've got a third law pair at the bottom of the rope and a third law pair at the top of the rope connected by the definition of tension. Now, the pulley then, it's not moving. And so the goal of the pulley is that the pulley is able to change the direction of force on the rope. And so it changes it by sort of doing this, rotating it that way. So this is the tension of the rope on the pulley again. All right, and then you got another third law pair, pulley on the rope. That activates the definition of tension. So we got the tension force of the wall on the rope. And then finally, all this was really meant to show that the tension vector of the rope on the wall is equal to mg. So you can go through each one of these forces, starting with the gravity of m, balanced by tension of the down rope, making a third law of the rope feeling a downward pull, but then it feels an upward pull at the top from the pulley. But that upward pull is rotated to a sideways pull by the sideward rope on the pulley, and then it keeps going until you're left with that result. And so this might seem obvious, but the point is that the pulley is able to change the direction of the tension. And it's always going to change the direction of the tension in the direction of the rope. Okay, so let's look at several different simple examples of this. And this is certainly a place where the signs, the algebraic signs that you use in your equations will be important. Okay, so we're going to do something called the Atwood's machine. Maybe you've seen it before. It's more of an kind of older way to find the acceleration due to gravity. And it is two hanging masses over a pulley, that's had a support at the very top, right? So we got pulley, and then we got a mass on one side, a mass on the other. There might be some quick check questions in the PowerPoints related to this, but let's make this a 1 kilogram block. Let's make this a 2 kilogram block. Sorry if that's kind of hard to read, but you got a 1 kilogram block on the left, 2 kilogram block on the right. Rope is massless. Pulley is massless and frictionless. And so the question is, what's the acceleration? This is a little bit too much to the right for me, so I'm going to, I can't select, okay. Where will be the best spot for it? Yeah, I need to move it. Move it a little bit. Okay, I should have enough room now. So let's look at the force diagram, or the free body diagram on each of these blocks. Again, it sounds like a silly point, but if the rope and the pulley are both massless, then they don't have any measurable forces acting on them in the sense that they don't need a free body diagram. So what we'll do is we'll draw a free body diagram for one, and probably only need to work in one coordinate, y, and then y for the block 2. So forces on M1. Now, okay, before we establish the free body diagram, it's helpful to figure out the kinematics. That is, it's helpful to figure out the motion. What's going to happen? What's going to happen when I release these two blocks? Most people will probably say, well, 2 kilogram block will move down and 1 kilogram block will move up. That's certainly true if they're released from rest. What if block 2 was already moving up and block 1 was already, like if I shoved, what would happen if I shoved the 1 kilogram block down? Well, then 2 would move up and slow down, right? And then block 1 would move down, decrease speed, and then move back up. So all that to say that the A sub 1 points upward, yeah, and A sub 2 points downward. So that's going to activate Newton's second law, and we're going to have Fnet of 1. Sorry, I need to get better handwriting for these examples. Yeah, that's better. Fnet of 1. Okay, and then Fnet 2 will be downward because, let's check in the chat real quick, but yeah, because that activates Newton's second law. So we automatically know that. So Fnet 2 points down. So what about in the what about the forces? Obviously, the forces now are on block 1 are tension and gravity. So we got M sub 1 G down. And then the tension, and this is the trick about this example, is that the tension, since Fnet points upward, the tension vector has to be bigger than M1G. And if you assume that all this stuff is massless, that is, if you assume the pulley and the ropes are part of the environment and they're massless, then the tension on the left is the same as the tension on the right. But you see here, they're not action-reaction pairs in the sense that they don't point in opposite directions. But of course, like we had just explained a minute ago, if you include all the action, if you include the pulley and the rope as part of the system, then, I mean, there's going to be tons of forces, tons of those little reaction pairs. You'll still end up with the same result. So tension is the same for 1 and 2, and it's smaller than gravity on M2. Because Fnet for 2 has to point down. And so that's the free body diagram. We usually don't draw those interacting object diagrams. It would be pretty simple. But let's sum the forces. So the notation that I'm going to introduce for here is like parentheses and then a letter, and then parentheses and then a letter. So parentheses 1y represents the sum of the forces in the y direction for block 1. Sum of the so parentheses 2y is the sum of the forces in the y direction for block 2. And of course the x direction is ignored, and so here's where the signs become very important. Oh, one last thing before we jump into the free body diagram, or before we jump into summing the forces. There's something called an acceleration constraint. Again, this is mentioned briefly in the videos, but it's really something that you have to practice. Okay, what is the acceleration constraint? Well, in most of these examples, the rope is fixed in length. It's flexible in the sense that it can rotate over the pulley, but other than that, it's not going to sway or it's not going to wobble in this sample. So basically, the length of the rope stays constant. There's a more complicated way to do it, but really, in this case, you're just writing a relationship between the vectors. You know that if one's accelerating upwards, the other one's accelerating downwards. And so in our coordinate system, the constraint would be written like this. A sub 2 in the y direction equals minus a sub 1 in the y direction. That's the acceleration constraint, because the magnitudes are equal, and yet the directions are opposite because of the pulley. So that really should give us a sign, that should give us a clue as to the signs of A. So now we can sum the forces, 1y and 2y. So 1y is going to be T minus M1G equals plus M1 times A. It's not M1 plus M2A. It's not this. It's just plus M1A. Okay, and now 2y, we got the same tension minus M2G equals, and here's the important thing, minus M2A. That minus sign causes more trouble for students probably than anything in this chapter. As complicated as these problems can get, those minus signs can be very tricky. And so that's why we have this so-called acceleration constraint, so we can handle these complicated, or these signs. Right, and so we can do this problem quantitatively if you like, and usually what we've got, if we know the masses of the objects, and we know what planet we're on, then we can find that our unknowns are tension and acceleration. So you can even write this out in numbers. This would be like T minus 9.8 newtons equals 1A, and then T minus 19.6 newtons equals minus 2A. Right, so that's a simple system of equations, two unknowns that you're trying to solve for. I think it's helpful to do the algebra with just the symbols. And let me show you what happens when you do that. The easiest way to solve this pair of equations is to, well, it depends on what you're trying to solve for. If you're trying to solve for acceleration, I'm going to subtract one of these two. I'm probably going to subtract, like, you do 1y minus 2y. What are you going to get? Well, the t's will cancel, and you'll have minus m1g plus m2g on the left side. That'll equal, on the right side, it'll be plus m1a plus m2a. And so you can factor out the a and divide by everything else to get the answer for acceleration. So acceleration ends up being m2 minus m1 over m2 plus m1 times g, which in our case, for a 1 and a 2 kilogram block, the acceleration ends up being g over 3. Because it's 2 minus 1 at the top, 2 plus 1 at the bottom. And so it's g over 3, which is 2.94 meters per second squared. So simple example involving ropes and pulleys. And this is really a starting point to a whole sort of class of examples that are really fun to kind of see how you can really just almost not write the acceleration immediately, but they're all really, really good practice. So if that is what we want to do, then let's continue and now add a surface. So the next example takes one of the blocks and puts it over a surface. And this is called a modified Atwoods machine. Let's say the surface is flat. And for now, let's say it's smooth. So we'll have, say, M2 on the surface, M1. Right there. Okay, so this is a pulley, same thing. Okay, if this is smooth, then you can do the problem almost the exact same way. The free body diagrams are pretty straightforward. So if it's smooth, right, then you've got A sub 2 accelerating to the right, A sub 1 accelerating downward. Okay, so what is our acceleration constraint? Well, again, we're relating the components of each of the accelerations to each other, right? And so if we're going to work in our standard XY coordinate system, which certainly that's what we'll do, we have X and Y for block 2, and really just Y for block 1. Then you have plus A2X equals minus A1Y. And again, this acceleration constraint is just here to make sure we get the minus signs right when we sum the forces. But let's look at the free body diagram. Okay, for block 2, we got M2G down. I would just write, you can just write N in this example, but if there are multiple surfaces, you might have to write like an N sub 2. And then T, which gives you Fnet 2. And then for block 1, again, here, the Newton's third law seems even stranger because the blocks or the tension vectors aren't even in the same direction, much less equal and opposite. But they're still equal and opposite by that argument from earlier in the conversation. But M1G, it has to be bigger than tension to make Fnet down. Oops. Yeah. Now, a quick thing to ask yourself is a conceptual sort of checkpoint is, how do the Fnets compare? Are the Fnets equal, or does the bigger one have a bigger Fnet since it's larger? Does the smaller one have a larger Fnet because it has a smaller mass? And it turns out that Fnet of 2 is bigger than Fnet of 1. Why is that? Well, they're both equal to their respective masses times acceleration, but the accelerations are the same. And so Fnet, looks like I didn't really draw this to scale as well as I could have, but looks like Fnet 2 is actually twice as big as Fnet for 1. And so let's sum the forces real quick. We got 1. Now we have 1y. Now we have 3 equations and 2x, which we don't really need. We don't really need 2x for this example, but still helpful to write all these things down. So we got 1x, 2x, and 2y. Some other semesters I would just type it out on Zoom, but it's still better for me. I still like doing it like this. So we have this 1y. We got t minus m1g equals minus m1a. All right, 2x, we've got t equals plus m2a. Okay, right? One of the steps that I'm sort of skipping is that this technically equals m1 times a1y, right? And this one right here technically equals m2 times a2y. But you see that acceleration constraint, if the magnitudes are equal, you can just drop the subscripts and make sure the minus sign's in the right spot. And then for 2x, we don't really need it, but it's n minus m2g equals 0. Good. So we got the forces summed, and we've got and again, usually the problems will involve the tension and the acceleration being unknown. You'll usually know gravity, and you'll usually know the masses. And if there's friction, you'll be given the friction coefficients. I'm usually one that likes to do the acceleration. So yeah, and then so you can show that the acceleration here is equal to, I'm just, in the interest of time, I'll let you verify that. If you take T1 and T2, again, if you subtract these two, that more or less gives you the answer. Yet acceleration equals, the magnitude of it is m1 over m1 plus m2 times g. And that's a magnitude. And you'll find for these problems with ropes and pulleys and frictions and normal forces that the acceleration is usually some function of, let's see, how do I describe this? Some function of the masses, including the coefficients and like some g. It's some function that looks like this. Really, it actually will look something like this. It'll be g times the sum of the masses on the bottom times, something. F of the masses, coefficients, maybe the angles, if there's angles in the surfaces. That's the general sort of expression for the acceleration. So every problem in every one of these shapes, in some sense, will give us a different formula for A. And then, of course, tension is a little bit harder to find. In this case, tension is pretty straightforward because you just multiply by m2. Tension equals m1, m2 over m1 plus m2 times g, the magnitude of the tension. All right, so several different options here. And so we'll, now really we're, with this example, what if we were to add friction? You can show that if you were to add friction, then that would just make a little, going back to this free body diagram on the far left, that would just add a little friction force right here, right? And that would actually, let me just, this might be a useful time to use a different color pen just to show, what color should I use? Oops. Okay, so if we add friction, let me do this. This might be kind of fun. So adding friction, so we got the little rough surface here. And so that is mu sub k. Got a coefficient mu sub k. That's going to add a friction force backwards. This is fun. I never used colored chalk when I was on the chalkboard. But that's going to make this equation here, the 2x, well, it'll make it t minus mu sub k m2g, because mu sub k times the normal force, still equals plus m2a. And so that'll change the formula. And instead of just being m1, over m1 plus m2g, the acceleration will be, where should I put it, well, you can follow along if it's, it'll be M1 minus mu sub K M2. Sorry if that's kind of hard to read. In fact, I can just, let's see, I can, oops. Yeah, what I can do is I'll just erase the M1. So when people are going back on the video, they can just see that where it gets corrected. Right, the formula for acceleration just changes like that. It just ends up being M1 minus mu sub K M2. So just adding friction changes that result, and the friction, or sorry, the you know, the tension responds as well. The tension changes as well, but you can see how just that minor adjustment, where that minor adjustment changes the entire problem. So with that in mind, that's a good place to stop. And we'll continue with this in later lectures. We'll certainly continue with this, make some harder examples, and see how weird tension and pulleys can actually be used for like leverage and counterweights and all these other examples. So we'll continue with that in the next video.